Jai Hind to all. Today I am here to present the video lecture of subject Digital Signal Processing BEC 503, and this is the third lecture of the series, and the topic is designing of FIR filters. And I am Dr. Amit Garg, Associate Professor in EC Department of Akgec Garg Engineering College. So let us start with the FIR filter designing methods. So first of all, we should know, before starting this, we should know what do you mean by FIR filters. So FIR filters are those filters wherein the output of the filter depends upon finite number of impulse response values. Okay, so if the impulse response values are finite, only then we can design the FIR filters. Another thing that FIR filters are generally, if you will talk about the realizing part, so these filters are realized using non-recursive techniques. And in filter designing of FIR filters is not so easy. This is a complex task, you can say. So there are various methods by which we can design FIR filters. So these methods are Fourier series method, window method, frequency sampling method, and optimum filter design methods. Okay. So out of these four methods, we will concentrate over here only on window method. Okay, because this is the part of our curriculum. So that's why we will see only the window method here. Okay, so let us start and know what do you mean by this window. Okay, so window technique. So the frequency response of a digital filter is periodic with period equal to sampling frequency. This you know. Okay, means if you are going to draw the frequency response of a digital filter, it will be periodic. Okay, so if you will see, then in that case the desired frequency response of a FIR filter can be represented as Hg e to the power j omega equals to Hgn e to the power minus j omega n. Okay, so you can say this is nothing but the equation like frequency response is what? In this case frequency response is nothing but the discrete time Fourier transform applied over the impulse response, and wherein this Hdn is nothing but our desired impulse response. And always the desire is to realize our desire is to design a ideal filter. So we will assume it that it is the frequency response for an ideal filter. But you know, because IR filters are non-causal in nature, and we cannot realize it, and or you can say those filters are not physically realizable. So we have to find out some method by which we can find out the finite response value, so that we can design this filter. Okay, so this is you know, this is the synthesis equation, and this is nothing but the analysis equation. By this equation we can find out the impulse response values corresponding to this frequency response. Okay, the limit is minus pi to pi, because you know the DTFT is repeated itself after a period of 2 pi. Okay, and you know the spectrum of DTFT is continuous in nature. So if the spectrum is continuous in nature, then in that, so that we have put integral over here. Okay, here is the summation, because our impulse response is basically the discrete, that's why we have put summation over here. Otherwise and this Hdn is nothing but, you can say, continuous, so that we have used the sign of integration. Okay, so now if you will see this Fourier series representation, so the Fourier coefficients of, if you will see the Fourier series representation for this, then the Fourier coefficient of the series Hdn are identical to the impulse response of a digital filter, that I have already said. But there are two difficulties with the implementation of this equation for designing a digital filter. First, you know, in this case the impulse response is of infinite duration, and another problem is that this is non-causal. You can see here the limit is from minus infinity to infinity. So there are two difficulties. One is its nature is non-causal, and another difficulty is that it is of infinite duration. So what happened? Non-causality is not a big issue if our sequence is of finite duration, because we can always provide a finite amount of delay to start it to make it causal. So the main challenge is that we can that by a method we can truncate this infinite duration sequence into finite duration sequence. because after getting a finite duration sequence, even if it is non-causal, then you can make it causal by simply providing a delay, so that it may start from 0. Okay, so this I have written over here. Now what is window? So let us suppose we are having a function which is of infinite duration. Okay, and we want to analyze, or we want to make a filter which is a FIR filter. Sorry, I have make it continuous. Actually, it is discontinuous. It is expanding from minus infinity to plus infinity. Okay, but it is of infinite duration. So what we can do? The function of window is that we will choose a window. Window is nothing but a mathematical function which will be overlapped with this signal like this. Okay, so when it is overlapped like this, so we will see only these coefficients of infinite duration impulse response. And how we can obtain these sequences? We will multiply these sequence values with the window function, and your window function may be of different types. That may be of rectangular shape, that may be of triangular shape, that may be of you can say raised cosine type of form, and there are so many types of window functions. So here we will analyze that what type of filter or what is the characteristics of the filter we are getting when we are applying different types of window functions over this infinite duration impulse response. Okay, so this I have written here, the infinite duration impulse response can be converted to a finite duration impulse response by truncating the infinite series at n equals to plus minus m. So it means after truncation we are having the coefficients only from minus m to m, where m is nothing but a finite quantity. Okay, so what happened if we will talk about the window functions? So there are so many window functions, but the general window function is rectangular window function. So rectangular window function, what is the role of rectangular window function? Rectangular window function simply truncates the infinite duration impulse response series. So what happened? Because of abrupt truncation, you can see it is written over here, but this results in undesirable oscillations in passband and stopband of the digital filter. Why it is so? It is because of abrupt truncation of infinite duration impulse response, and you can say this is created an effect which is called Gibbs phenomenon. Okay, so this is due to the slow. Why it is happened? Why we are getting passband and stopband due to abrupt truncation? Because this is due to the slow convergence of the Fourier series near the point of discontinuity. So these undesirable oscillations can be reduced by using a set of time varying functions W, and W is nothing but the window function for which I am talking about, referred to as window function, to modify the Fourier coefficients. So window techniques we can illustrate it in this particular figure. Here are the figures. Here left side figures represent the time domain representation of the signal, and here right side you can see the frequency domain representation of the signal. So let us suppose we are having an infinite duration impulse response sequence which is from minus infinity to infinity. Okay, so if you will see the impulse, the frequency response of this infinite duration impulse response series is like this. Okay, it will extend it from minus pi to pi, and it will be periodic. It will be periodic again from minus pi to pi, and you can say from 0 to 2 pi. It will be periodic. Okay, and this is our window function. So we have taken a generalized window function. So we can see the length is minus n to n. This is the length of the window function, and because the minus value is there, so there are two types of window functions. One type of window functions are symmetric window function, another are causal window functions. So whenever your window function starts from 0, we can call it causal window function, otherwise we will call it as symmetric window function. So this is symmetric window function. So what we are doing over here in time domain, we are getting the result. So you can see the result, only those values of HDN we are getting over here, wherein wherein there is some value of window function. Where the value of window function is 0, we are not getting any output. So that you are having Hn, which is nothing but the truncated impulse response series by a window function. Okay, so as you know that the operation that is performed in time domain corresponds to convolution in frequency domain. So here the operation is multiplication, so that we are getting this, and here the operation is you can say convolution. So this is nothing but you can say we are assuming that the frequency response of this type of signal is somewhat like this. It is of sync type. Okay. So if so, it means this we are getting when we will convolving this HDE to the power j omega with, this is the sign of convolution, with WE to the power j omega. Okay. So this is the time domain representation and this is the frequency domain representation. Okay. And because you can see here this is basically, you can write it like n minus 1 by 2. Okay. So but because we have already seen that impulse response that is non causal in nature is not realizable. Okay. So for making it realizable, what we are doing, we are delaying this sequence by an amount n minus 1 by 2. Okay. By an amount by an amount n minus by an amount n. Okay. When you will delay it by an amount n, so that it will start from here. Okay. So this is also n. Okay. Now what about the Fourier transform? So if you will see the Fourier transform of window function, if we will talk about the Fourier transform of the window function, it consists of a main lobe, this is the main lobe, and others are side lobes. And the what should actually happen? This main lobe width should be as narrow as possible, but its height should be large. So a good spectrum is one in which most of the energy lies within this major lobe, and very less energy is you can say wasted in these side bands. Okay, because this is the spectral leakage. So what we want with our spectrum, a good spectrum is one, a good window spectrum is one in which most of the energy is concentrated around this main lobe. Okay. So this I have already explained this operation, how we are getting Hn in time domain. When we will multiply Hdn with Wn, we are getting the sequence Hn, which is of finite duration. So this I have already explained all this. Okay. Now this is another aspect. This is another aspect is like what? Here we have seen that the window or here we have seen that the window that we have taken is rectangular window function, due to which a phenomenon occurs which is called as Gibbs phenomenon. Why it is happened? Because the slope of rectangular window is infinite. Okay. So it is found that if we will not truncate this series, infinite duration series, using a window function which will abruptly truncate, rather than if we will choose a window function which will truncate this infinite duration impulse response with some gradual truncation, not abrupt, it is gradual. So the gradual truncation leads to the transition bandwidth. Okay. So this is the phenomenon written here. A major effect of windowing that the discontinuities are converted into transition band between values or on either side of discontinuity. So the width of these window, these transition band depend on the window of the main lobe. A secondary of window effect of windowing that the ripples from the side lobes are produce approximation errors or W. So it means what we want to say simply, if we are choosing a rectangular type of window, so we are getting Gibbs phenomenon due to abrupt truncation. But if we will choose another type of windows, like this is your initial rectangular window, after that let us say we are having Hanning window, which is shape is like this, then you can say Hamming window, which is also somewhat look like this, but these are mathematical functions. So you will see the mathematical function, then you can find out the difference. And the last window you can say is just triangular window. So as soon as we are moving from here to here, we can see that truncation will become more and more gradual. And if the truncation is become more and more gradual, in so that your transition bandwidth gets increased and increased. Okay. So transition band, when transition band increases, so what happened? Because it truncation is gradual, so in that case the side lobes that are generated will become less. So here there is a trade off between the side lobes, number of side lobes, and the transition bandwidth. If you want to get less number of side lobes, then your transition bandwidth will be more, and vice versa. Okay. So you have to always trade off. That's why we are studying so many window functions. Okay. So let us move to the rectangular, move to the window functions. So this is the first window function, rectangular window, which I have already told you. So you can see this is a rectangular window function. This is non-causal or symmetric window function, which is lying between minus n minus 1 by 2 to n minus 1 by 2, and the value is 1. Like this, simply. This is important thing is here that this value, if is minus 3, then it will become 3. Means it is always symmetric. No, it is non-causal, but it is also symmetric. You can see from here. Okay, and 0 is always here. And another aspect of taking this window symmetric, that always the coefficient within the window function will become odd because of this 0. Okay, and this is our causal window function. The function starts from 0 till n minus 1. Okay, another one is modified rectangular window function. So because of this phenomenon, we are trying to move to other window functions. So first window that we have chosen is, let's say, modified rectangular window function. So modified rectangular window function is almost similar to rectangular window function. As one only the difference is that last sample value which we are taking, we have made it half. Means in this case you can say, if all these magnitudes are 1, so this magnitude will become half. Okay, so this is your modified rectangular window function, and we found that we are having only, you can say, a little bit of you can say better results with this modified rectangular window function. Then Hanning window function came in the existence, and again this is a causal Hanning window function, and this is non-causal Hanning window function. You can see the coefficients which we have taken over here are similar, coefficient values are similar, and here it is from minus m minus 1 by 2 to m minus 1 by 2, because it is symmetric and it is from 0 to m minus 1. And in case of Hanning window function, the main lobe width is approximately 8 pi by m. Okay, and the first side lobe is at minus 32 degree. Another window function is Hanning window function. What happened in case of Hanning window function? We can see that first and last window coefficients are 0. Okay, so basically Hanning function is slightly different from it, that they have made this coefficient, rather than 0.5 they have made it 0.54, and rather than 0.5 it will made it 0.46, so that the first and last sample values are not 0, but it will become the difference of these two. Okay, it means 0.08, and so this is the expression for causal Hanning window function, and this is for symmetric Hanning window function. Okay, then another one, Blackman window function. So it was seen by the Blackman that by adding an extra cosine term, we can further reduce the side lobes. Okay, so that's why Blackman added one extra cosine term as compared to Hanning and Hanning window function in this, to get lesser number of side lobes. Okay, but again when we are trying to reduce the side lobes, as I have already told you, transition bandwidth increases, or the width of the main lobe increases. So these are the functions for non-causal, and this is for causal Blackman window function. And you can see here the main lobe width is 12 pi by m, and the peak of the first side lobe is at minus 58 degree. Okay. And then Bartlett or triangular window function. In this case, you know, the shape is triangular, means you are having this I am just drawing the envelope, otherwise the sequences are like this. Okay, so this is symmetric window function, symmetric triangular window function, and this is symmetric, this is causal triangular window function. And in this case we have found that triangular window, being reduced from, in case of rectangular window, the side lobe value is minus 13 dB, and in case of this it is minus 25 dB. So less number of side lobes can be there, and the main lobe width is 8 pi by n. So you can say or twice that of the rectangular window. Means when we are using triangular window in place of rectangular window, then what happened, our transition bandwidth gets twice, although we got the reduction in side lobes. Okay. So this is basically the comparison. You can see the comparison between all these window functions, rectangular, Bartlett, Hanning, Hamming, Blackman. You can see the transition bandwidth. You found the transition bandwidth of Bartlett, Hanning and Hamming windows are same, 8 pi by m, and the lowest one is 12 pi by m, because transition bandwidth is inversely proportional to m. So that's why you can say this is the for the same filter order you are getting the largest transition bandwidth with this Blackman filter. Okay, but you can see, if you will see the minimum stop band attenuation, so you can see the maximum attenuation in this value is -74. It means the lesser number of lobes are found in case of Blackman window function. So these are all the window functions. You can see the shapes, and this is the rectangular one, and this is basically the one that is starting from here. This is Hamming. One it is starting from here is Hamming, and this is Blackman. Okay, and this is nothing but the triangular one. Okay. Now we will see how to design the FIR filter using window techniques. Okay, so we will see one problem here, that how to solve the numerical given. Okay, so first of all we will choose the desired frequency response. Either it is given to us or we have to find it. Okay. Then we will take the inverse Fourier transform to get this desired impulse response HDN. Okay, then we have given a window function, that design an FIR filter using that window function. So we will choose that window function. Depending upon this frequency response, we will choose our window type, that whether we have to choose a symmetric window or whether we have to choose a causal window. Okay, we will choose a causal window when this frequency response is also started from 0, means already it was delayed by an amount e to the power minus j omega m minus 1 by 2. Okay, where m is the filter length. Okay, so choose a window function, sequence wn and multiply by HDN by wn to convert infinite impulse response to a finite duration impulse response Hn, and then we can take the Z transform to get the Hz, or we can also obtain the frequency response by simply putting Z equals to e to the power j omega. Okay. So here is the question, we can see. So here we have given the desired frequency response e to the power minus j2 omega and 0, and you can see this is from minus pi by 4 to pi by 4, and you can see this is somewhat like this. This is somewhat like this. So this is what type of filter? This is basically a low pass filter. Okay, so even if it is not mentioned over here, you have to assume you have to find that which type of filter is this. So this is low pass filter, because within this range, means from minus pi to minus pi by 4 and from pi by 4 to pi, the value is 0. Okay, and we can find out the filter coefficient HDN if the window function defined as, so here it is rectangular window function, because you can see all the coefficients are 1 between 0 to 4. And also determine the frequency response. So what we will do first, we are having this desired frequency response. We will do the we will find out the HDN by using this formula. This formula we have already seen. Okay, so we will put the value e to the power minus j2 omega, because this response is between minus pi by 4 to 4. So this limit will be changed from minus pi by 4 to pi by 4. Then we will get this term 1 by 2 pi minus pi by 4 to pi by 4 e to the power j omega n minus 2 d omega. Okay, then basically you will solve it. So after solving it, you are having this type of term, 1 upon pi n minus 2 sine pi by 4 n minus 2. So you will see, whenever you have given any window function, you are having this type of answer. Another important thing is that because of this term 2 is, you can say alpha is 2. So alpha is equal to m minus 1 by 2. So this value 2 you will find when the value of m will be 5. Okay, so here the value of m will be given 5. You can say here 0 to m minus 1. So if it is not given to you, even then you can find it. Okay, Now one important thing here, then that now what you will do, basically this is the value of HDN and you will change the value of n from 0 to 4 and find out these values. Okay, so you will see for all the values it is okay, but when n equals to 2, so you will find you are having sine 0 by 0 form, which cannot be solved like normal method. It is by it will be solved only by allopical method. So in allopical method, you have to simply differentiate the numerator and denominator and put n equals to 2. Put n equals to 2. So here you can see this will become cos pi by 4 n minus 2, and then it is pi by 4, and in denominator it will become pi. Okay, and now you will put the value, then you will get the value 1 by 4, and other values simply putting n equals to 0. Another important thing is that because FIR filters are having linear phase property, so the value of, in this case, the value of H0, let's say length is 5, so 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. So the value of, sorry, it is become from 0 to 4. So the value that we will obtain from here is the same here, same here, same here. Okay, so this 1 and 3 and 0 and 4 means HD0 and HD4 equal to same, and HD1 equals to HD2 equals to same. So that's why we have calculated these values and made it equal to this. Now we will multiply it by the window function, so it will become HDN into WN. So you are having this H0 coefficient, because window function, in case of rectangular window function, all the coefficient values are 1. So we are having the similar values of Hn which we have obtained for HDN. Okay. Now this we have calculated the frequency response. Frequency response is simply Hn into e to the power minus j omega n equals to 0 to 4. Then you will expand it, so you will get it. Now important thing is that the filter that we are going to design must be causal in nature. So what we will do, so it will only become causal when this e to the power minus j omega 2 will be outside, or you can say this term will be there in the frequency response. Only then your frequency response will become causal. So what we will do, we will take this term, initially we will take this term common, and after that we will convert like this. Okay, then the value of H0 is nothing but equal to H4, H1 equals to H3, and H2 is alone. So you can write it like this. Now e to the power j2 omega plus e to the power minus j2 omega will become, now you will put the coefficient values and this values, and you know what is the value of e to the power j2 omega plus e to the power minus j2 omega according to Euler's theorem. It will become 2 cos 2 omega. Okay, so you will put this value here. This will become cos 2 omega plus j sin 2 omega plus cos 2 omega plus j sin 2 omega. Okay, so you will solve it. Cos 2 omega plus j sin 2 omega plus cos 2 omega minus j sin 2 omega. So it will become 2 cos 2 omega. Okay, so you will put 2 cos 2 omega over here and 2 cos omega over here, and when you will solve it, you are having the frequency response of the desired filter like this. Okay, so this term signifies that the frequency response that we have obtained for the designed filter is causal. And this is, and somebody asks, if somebody asks the magnitude, so magnitude is nothing but, when you will take the magnitude, then the magnitude of this term will become 1. So what is the magnitude value? Magnitude value is nothing but this term. Okay, if you want to calculate the transfer function, so what you can do, simply Hz equals to summation n equals to 0 to 4 Hn z to the power minus n. So due to this, you can easily obtain the transfer function Hz. Okay, so this is how so this is the reference that I have taken for making this presentation. Thank you.